So welcome to this week's Origins Colloquium held jointly with the Astro Seminar at Chalmers this week. So it's a pleasure to welcome Lynn Dessin to give the talk for us this week. Lynn has graduated from KU Leuven in 2000, I think it was. She was a postdoc for several years at Leuven and also in Amsterdam. She then joined the faculty in 2010 at Leuven and is now a full professor there and director of the Institute. She's published more than 200 refereed papers and works on a wide range of topics from exoplanets to all stars and observational programs in infrared and submillimeter astronomy, as well as theoretical astrophysics. So a very broad range of topics. And she's been visiting Chalmers on part of her sabbatical, and so it's been a pleasure to host her here. We look forward to hearing about your work.
Thanks, Jonathan. Thanks for joining. Also, thanks to the people online who are joining. I've seen partly your faces, only a few of them. Indeed, it has been a pleasure for me to be here in Chalmers for a few weeks. I will come back to some of the projects I've been doing while being here at the end of this talk, but also for tomorrow's seminar that involves Stars Cook. I will tell you more about things I've been doing here. Now it's more a bit of a more general overview, since I know that people from different backgrounds are attending, and I always want talks to be accessible to the broad public. So today's talk will mainly focus on evolved stars, and I will try to bring you into some things up to the state of the art of something that we know, but also things that we do not know. And so the main insights come indeed from what Jonathan has been saying, insights from submillimeter astronomy. No, it's not. Okay, here we go. So we talk about these evolved stars. I should stand here. I cannot touch there. So I've used my mouse. I'm used to teach. I'm used to stand along.
Yeah, watch the camera angle there. Yeah.
I don't know where to get from.
You are there in there.
Yeah. So we talk about these evolved stars. These are these asymptotic giant branch stars. They are very luminous and have quite low initial masses, between 0.8 and 8 solar masses. So this is the focus of today's talk. What do we know about that, and why do we want to understand these things? Our sun wants to become such a late-night giant. Well, this is an image, and all the image of Hans Olofsson from this group, and this is Yukan. And you see that this is the image that has been dominating our view of these evolved stars for a long time. So in the center, you should envision it to be the star, and around it you see this huge circumstellar envelope created by its stellar winds. Now, if you think upon what is happening in such a stellar wind, this is a kind of simplified schematic that you can see. It's a 1D schematic. On top, you see some of the dominant chemical processes. At the bottom, then, the physical dynamic processes. So what is happening is these stars are pulsating. And so given the fact that the surfaces go up and down, you get collisions. And every time you get such a collision, molecules and also tiny dust grains tend to break up. So you get completely new chemistry ongoing. This is what we call this non-equilibrium gas-phase chemistry. It's extremely complex to model, and there are many unknowns there. However, what we do see is that somehow, and it's still magic, it's really magic, somehow these molecules can form dust grains. Dust grains are huge compared to a gas molecule, so you get the radiation pressure on them. It helps them to be driven out. The opacity is large enough. And while they drive out, they collide with all the little gaseous molecules, and they get also the gaseous molecules out. So this is the cause of your stellar winds. Stellar winds with mass rates around 10 to the minus 8 and the minus 4 solar masses a year. Typical wind speeds of a few tens kilometers per second. The outer region of your circumstellar envelope, there is where you have the photochemistry partaking. UV photons from the interstellar medium penetrate, and you have a very active photochemistry over there. This is our view and has been the standing view for decades upon these evolved stars. And why do you want to understand these evolved stars? Well, one of the things you would like to understand is how important are they when we want, for instance, to model the chemistry of our universe. These stars are known to be very active nuclear reactors. The newly created molecules and the atoms inside the hot cores are brought outside and they're enriched in the stellar medium. So what you want to know is not only the chemistry. I will not talk about chemistry today, but you also want to know the magnitude. How much is there delivered? And these are then the typical diagrams that you see. So these diagrams you see typically in function of luminosity, people are predicting mass loss rates. How do you deduce that? Many astrophysicists like simple relations. Why do we need simple relations? If we then go to complex, for instance, stellar evolution codes, such as MESA, you cannot do your ab initio modeling. I cannot say to MESA, this is my one star, and now let's do the full chemistry and physics of my AGB and put that into MESA and let it do a prediction for the whole of its evolution. So you need simplified analytical, in this sense, relations that you put then in a more overarching stellar evolution codes that can then be used to predict stellar evolution. So what you then are after is, okay, do we, from data, from theory, do understand what are mass loss rates? Can we predict that? And so how do we deduce mass loss rates for these evolved stars? Two main diagnostics. On the top rows, you see here images from Sophia Ramstedt, and also the second palettes from her. And these are gaseous molecules, carbon monoxide. Carbon monoxide, why this one? It's very stable. It is the second most dominant molecule next to H2, but H2 you cannot measure that easily since it doesn't have a dipole moment. So you take carbon monoxide, you model it. So one of such models is a red line, and the model gives you a mass loss rate. A gas mass loss rate. The second, the lower panel is, well, getting carbon monoxide lines is not too easy. They are not too strong. Well, compared to some molecules, they're still strong. I don't think that Jonathan would agree to me, but most often and much more easily is measuring their spectral energy distribution. And you see them little wiggles on top of that. And these little wiggles are amplified in the bottom row. These are the dust features. You model the dust feature, you get the dust mass loss rate, but dust mass loss rate is not yet gas mass loss rate. Then you need to multiply with a factor that is quite uncertain, at least with a factor of 10 uncertainty. It's around 100 to 1000. We'll go from the dust to the gas mass loss rate. You do that for many stars. You do that for many stars. For these stars, you at least hope you have information on masses, temperatures, and luminosity, and you get your mass loss rates. And then you turn the question around. You say, if I have the mass loss rates, can I then deduce an analytical relation with all of these input parameters? And you do your regression modeling. And you get of these relations. You see here two of them displayed, one by Jaco, one by Goldsman, 2017. There are various of such relations, most of them based on dust analysis, not on gas analysis. So let's go back to our quest.
And then the dust is forming in the wind.
The dust is forming in the wind is the cause for the gas mass loss rates, but is a factor of 100 to 1000 weaker.
It's very uncertain what the dust is doing.
Absolutely, absolutely. So your uncertainty on your gas mass loss rate is much lower than on your dust mass loss rate, but you have much more data for your dust. For the SED, I should say. So it's a game that is not perfect. I'll come back to that later on. So let's go back. I need this analytical relation. I've shown two of them here. What is there available in literature? What has been deduced? This is it. You see that it goes always. You see that, I didn't tell you that yet, but I have here the blue and the orange spots. Stellar winds are, when they are above roughly 10 to the -7 solar masses a year, they are high in rate than the nuclear burning rate, so they dominate your stellar evolution. So through that phase, I don't mind to match up a nuclear burning. I'm mainly interested, if I want to predict stellar evolution, what is the wind masses? So that is the difference between the blue and the orange vision. Now, going back to our question, you see here, the different symbols are whether they are theoretical, observational, or in between. But the main message here is they differ by orders of magnitude. The several relations you see, they differ in very important regions by 2 or 3 orders of magnitude. So then the question is to you go to MESA and you say, I want to model a star of 1.5 solar masses. Which wind masses will you choose? All dependent on which one you choose, you have another outcome. Or let's go to the red supergiants that can go into supernova. All dependent on which one I take, the same part of the red supergiant wins, I have either an explosion or not. So that's something that is inherently extremely uncertain in astrophysics, and it has a big impact. And then the question is, but why? Why are they so different? Uncertainties, as Jonathan was already touching upon, in the dust is one of the causes. But there are other causes as well. And that's one of the discussions today. Since I have started my talk with this image of Hans Olafsson of UCAM, nicely spherically symmetric. But is that the real eye of an aging star? We have now much more detailed data. And you see here surface convections at the size of one stellar radius. When we go to larger scales, we see that also the dust is not formed nicely in spherical symmetric shells, but you see clumps arising. You have at even larger scales. You see that's one example, the kind of a bipolar outflow. I'll come back to that because of that is probably that it has a binary companion. And then here the larger scale is the bow shock, something that Matthias Merkur is also working on, the collision between the winds and the interstellar medium, as your little duck that is going through the water. You get a classical bow shock. It implies that our way of modeling winds in a spherically symmetric way is just too inaccurate to give you a correct answer on wind mass rates. The framework that we have been doing our model, it's so easy going into 1D descriptions, is not true. We have to embrace, in a way, all of these 3D complexities, whether small, whether the big scales. Today, I will talk more about the bigger scales of the complexities, but we're also working on the small scale complexities. What about these bigger case complexities? Since this is one of the things that is very important, I think that almost none of the stars we are studying is alone. He or she or a hut or the or whatever has a companion. The reason I'm saying that is that we were granted with an homologue program and we wanted to study wind mass rates. And we thought, well, let's take a sample in strength of wind mass rates, etc. And we thought we never thought about binary companions. We never thought about that. We just imaged the stars. And this is one of these stars. This is Seraquili. And you can see this is the carbon monoxide line. When you would image it, it's a very normal and parabolic. You can model that with a simple spherical wind. But when you look to the data itself, the ALMA data, you see a lot of structures arising, all dependent on which velocity channel that you're at. This star is not a single star. We even have problems if modeling it with a companion. We'll see that later. This was part of our sample that we had. And well, that was the full sample at that moment. And when we looked at that sample, we did see all kinds of complexities arising, being in the form of a bipolar structure, a very nice boat-like structure, and here, a bit weaker, we have more classical spiral-like structures. That are the most easy things to understand from a binary companion. I'll explain, you just accept it. So you have these complexities, morphological complexities arising. And when I was making that graph, I did order them, but I did order them not in terms of how do they look like. I did order them from left to right and from top to bottom with increasing mass loss rates. And that's the funny thing. I ordered them, and by ordering them with mass loss rates, by ordering that with mass loss rate, you also see, for instance, that for the highest mass loss rates, we go more to a spiral-like structure. And the lower the mass loss rates are, the more complex the structures are. I don't understand that very well. Well, I do understand it now. I probably understand it then. So there is a correlation with your mass loss rate. Something with the wind mass loss rate has an impact on your morphology. So you have a correlation. A correlation is not the same as having the cause, but you know at least that there is some physics that we can go on. The correlation coefficient, which is expressed, was pretty high. And so we thought, okay, if this is a correlation, then we might have the cause for that. Since you know the answer, we talk about binaries. Binaries were already proposed for a long time. But binaries, in the context of planetary nebulae, the successors of the post-AGB stars, are often close in binaries and have very short periods, few days, 10 days, 100 days, not more than that. What I'm talking here about is not a star with a planet on a short orbit. Well, for me it's still short. There are orbits of, let's say, 2 years, 3 years orbits. They are at a few stellar radii. And so what is happening, officially we call them long period systems. In quite a lot of my proposal, I still call them short periods, but that's just nomenclature in your estimate and your words that you choose for that. But what are these stars doing? So if you have, sorry, I have to stand here, I'm not used to that. So if you have the classical picture of two stars, they either interact or they don't interact. If they are close one to another, and this is here to the right, they can have your contact binary, and then, for instance, one star can go via mass transfer, can feed on the other star. If they are detached, as here to the left, they live alone. It is as if they're not there. But we are here in this situation. It's still officially detached. The star's first lobes don't touch, but it is the wind of the giant star that is filling the Roche lobe, and that can be tunneled close to, it's not exactly, it's close to L1. We get a tunneling of mass from the giant star towards its companion. Okay? And so, as of that, and that is really thanks to Alma, the thing of having binary companions around evolved stars has again become a hot topic. And so, what do you see? So, what we have been doing is we have been looking into a lot of data, and you have seen several groups starting in modeling such as systems. And I told you that I would explain you a bit why do we see spirals. Spirals is the most easy thing to understand. You have two kinds of spirals that can form when you have these two stars with inverse overflow. One type is, so I just was explaining to you, you have the giant star filling its first lobe, it transfers mass to the companion. Meanwhile, that companion goes around its giant star, so it drags the material behind it. So you get literally a spiral attached to the companion, and it doesn't have a very high thickness. It is really confined towards the orbital plane. That's your one spiral. It is this one. You can see here. There is a second spiral. The second spiral is when your companion has also quite a bit of a mass. Your main giant is also wobbling around the center of mass. It's not standing still. That wobbling around the center of mass also is causing a spiral, since the star is not standing still. It is as putting a bit of milk in your coffee or some water, and you turn it around, you will see the spiral coming. There you have the gas giant losing its mass, and meanwhile it wobbles. You get a second spiral, and it is a spiral that has a very large thickness. It is almost touching your orbital axis. And at some point, these two spirals can collide, all depending on your geometry. You also get, around your companion, you can have the formation of an accretion disk. Literally, but you also can have Keplerian motion, the Keplerian disk-like structures arising. How that works is very much dependent on the physics that you put in and on a lot of assumptions. That's the challenge of the modeling. You will see that. Let's say, have in mind the main morphologies. Why did I say to you, low mass oscillates are complex, high mass oscillates are spirals? Did I say that to you? It's not really mass oscillates, it are velocities. A low mass oscillate is often also has a low expansion velocity of the winds. A high Masslow's rate has a high expansion velocity. And now think we have this high Masslow's rates, you have this wind particle, and here is your companion, and there it is, the wind particle, and oh, there is a companion. It doesn't mind too much, and its speed is too large. When it has a low speed, it has much larger interaction probability with your companion. So the lower the speed of your particle, the more interaction probability you have. You can even quantify that in your Bonnier accretion radius, the larger that will be. So the more and the more complex your morphology will be. So this is why I accidentally, the first had that order. It was not an order in Masslow's rates, it's dominantly an order in velocities. So,
what fraction of the mass is being accreted versus lost?
oh, can I come back to that?
Mm-hmm.
Yeah,
sure,
we are trying to model that, and it's one of the most complex things to answer. I'll show it. I'll come to your question. It's a good one. We are also not trying, we did see all of these nice things. We're trying many ones now. So this is for a triple system. I do show that, and it's just a nice image. It's kind of almost a snake-like structure that you see here. So here you have hierarchical triple systems, two close to one another, and one further out. And then you see this kind of ring structures. It has been used for an art exhibition. This image. That's nice. Now, this one, I show that one. This is one made with phantom. That's an SPH kind, and it's an SPH, a smooth particle physics modeling approach that we use. We also use grid-based approach. And you will ask me why? I'll tell you. Why do you opt for a grid-based approach? Grid-based is literally, I design my Cartesian or spherical grid and I put in my activity. And then you let it thing evolve. Well, SPH is a completely other way of thinking. SPH-based, the one that you see here, is much better when it comes into angular momentum conservation. It has inherently the conservation loss. Putting that in a grid-based code is much more trickier. The good thing about grid-based approaches, and that's one I will show you here, is that it's much better off when it comes into instabilities, radial instabilities, Kelvin-Hamilton instabilities, shocks. Then you have to use a grid-based approach. And so the model that you see here is a model, it's a grid-based. MPI MFAC means grid-based approach for me. Cron is a chemistry. That's something that Jonathan will also know. That's a chemistry code that we could do. And here we have this AGB star. I will start to move. Wait. The movie. Is it one start? Yes, it does. So we have the AGB star that is pulsating. It does like that. You have the companion over there. And it creates its own little molecules, its own little dust pieces. As such, it creates an initial stellar wind. And then you start seeing how this is density, this is carbon monoxide, this is temperature. And here to the right, you have your carbon monoxide predicted line profiles. You see that I see many things, all depending on which velocity I'm after, all depending on the inclination of the system. And so you can then think backwards. If this is model predictions, and then you have your data, how to match one with the other. Then you see so many structures there. So you cannot easily tell these are the data, this will be null, or this will be the retrieved parameters. You still are too much in the plane of, there are so many things going around. We see so many structures. How can I match data with models? I was saying this is grid-based. That is an important aspect here. I was telling you I have grains that are forming. As such, I can predict the masses. And then the question is, can a partner change her life? Normally it does. He or she does. It's also here. Can a partner change your mass loss rate? If we do this simulation, binary companion is only half a solar mass. It is even at 10 AU. It's quite far away. Then I have a predicted mass loss rate of around 5 times 10⁻⁶ solar masses a year. Now let's do the same thing and just delete your companion. what mass loss rate do you then have? Without the companion, your mass loss rate decreases with a factor of 6, 7. You can see here. So a companion is increasing your mass loss rate. And then think upon my first graph with all these lines which were different by 2 or 3 orders of magnitude. They all have modeled the data, assuming no companions being present. But this implies that all of these mass loss rate relations are wrong. Since many of the stars that have been analyzed then, and I mean with many, this is at least 50 to 80% of them, have a companion that can influence the mass loss rates. So any of the relations that once have been made, we cannot trust them yet. They're overestimated, and they are just used as that in single-star evolution models. So these predictions are just not correct. Look, for instance, at this one. That's a graph I recently made. This is the mass loss rate prediction of Fasiliades and Wood. This is the one that is most often used in MES and all kind of stellar evolution codes of the Australian group. They also use Fasiliades and Wood. This is really a very good paper, 1993, and these are many of the stars that have been used there. What I have done is have taken this data, and I now have indicated whether they are Myers or semi-regular variables, whether I have a convincing evidence already of a binary, or whether I have a binary candidate. The candidate comes from the fact that I see very strong UV or X-ray emission that can come from the accretion disk. And you see that most of these stars are suspicious. So if I delete, I don't say that these ones are not suspicious. I don't have the data yet. Yeah. So this is just a graph to show you how uncertain and also how wrong we are. It's not only upon accuracy, it's also upon precision. We are wrong. We have this mass loss rate not correct. And if we now lower our mass loss rates, what is then happening? Well, then you can do it's a kind of a boom-ups. It's a very nice thing. You say, okay, let's lower mass loss rates. Then you will know that you will have more nuclear fusion on the HB. You will have a brighter HB FIP. You will have more redshift. And then you can continue your discussion. I will not go into all the details here, but you can do predictions about the white dwarfs, about planets that can form, about chemical composition, etc., etc. So lowering the mass loss rate of an old star, for some people a bit of a boring star, has a huge impact on our understanding on planet formation, galaxy enrichment, etc. But okay, there is a problem how to tackle it. Well, there is one but crucial example I can give you here. I cannot say which one it is. It is in Press for Nature Astronomy, but I show it already to you here, and it will not be broadcast. This is at least what Jonathan promised me. So this is in press now. We have been through the proofs last days. This is data that we have taken in 2019. And you see here in 2019 ALMA data. This is the continuum that you have. And you see here a bright blob and you see second blob. This is the star itself, and then this one we were not sure of. Is that just a dust clump? It's dust continuum that is expelled and that then would travel outwards in a radial way? Or is that potentially a companion? And then you would think upon it should have a Keplerian rotation around your star. In 2019, the quest was open. Okay, we have seen a secondary blob. What is it? When for you BESAT working on VYCMA, etc., we automatically will think, oh, well, there is another blob there, another dust blob. We were keen on having a companion there, but we were not sure. So we have waited a few years, and then we got a second data set. This is shifted, and it's just only shifted with accounting for the proper motion. And so you see here again the HB star, and you see that the secondary blob have moved its position. And then I have combined that with other data. So you have now the ALMA data sets. Here is the Gaia position of the HB star. You also have a Gaia Hipparcos position in 1991, and written a Bayesian orbital inference code to model the whole thing. And this is what we get out. So you see here in this movie how you have the position of both stars. We do not only have it how they turn around one another, but also the proper motion we have deduced. And you can see how M1 is the HB star. You can see its trajectory through time in the sky. And you also can see M2, the dotted line, its trajectory through time. So having these data sets gives us a unique opportunity to solve the full orbital solution. So it is not as, for instance, with radial velocity curves that you have your M2 sine I, that you don't know the inclination. Also, I have the sine I. I have everything. You have such a high astrometric accuracy that you can do and play with things. It was going back to orbital mechanics, but it was very fun to do that. Yeah? It was playing with all your angles and having it correctly done. I will not discuss this thing. So what we have for that system? The full Keplerian solution. We know M1, we know the mass ratio, we know the optical saturation, eccentricity, inclination. I don't mention these two ones, otherwise you would know which star it is. Yes, we know the distance and also the proper motion in alpha and delta. It's not really slightly non-eccentric. It is, if you do the Bayesian stuff correctly, you can prove that the eccentricity is not significant. So you have a circular orbit in this case. And that will be a nice thing. It's a circular orbit. We have done the whole thing also together with the people with Amanda Caracas. I have given her the pulsation periods of the star, luminosity, temperature, and they have used that information for their codes and see what could be initial mass and what is the current mass of the system. So that's fully independent. Here I have the dynamical mass. And you see that there's a slight tension between that. And then the slight tension is good. Well, it's good since it tells us something about potential missing physics here. For instance, what is very uncertain in the stellar evolution models is the overshooting parameter. So we hope that in the future, by having more data, we do not only improve on our understanding of binary physics, it's also our understanding of stellar physics. How does a star, what is the internal structure of a star? We have seen also around the star its accretion disk. So that's the star, that's a companion with its accretion disks. What you see here, again, we go back to the phantom SPH models. I have put in from the data the mass loss rate. I cannot do that inherently predictive here. It's an input in phantom. And then you compute your accretion disk. You can compute its disk mass. That's the gas disk mass in the accretion disk. When I check that with what I get from the data, that's the dust disk mass. You see a factor of 100 difference. That's all nice. That's roughly the expected dust to gas ratio that you have. And then there we go to Jonathan. Then you can play the game. I have data, I have an eccentricity, I have an orbital situation. What will be the future of the system and what was its past? And so you do your orbital evolution calculations. For this kind of systems, if you do that, there are only two things that are important. What is the impact of the wind on your orbital separation and the impact of your tidal interactions? And this is work done by my PhD student, Mats Esselders, who has been working a lot on these tides since we have implemented new tides physics. So not only equilibrium tides, but also dynamical tides for these evolved stars. When you reshuffle all of your equations, then Jonathan, you see here the mass accretion efficiency, that's our beta. And you see the angular momentum transfer, that is our eta. How do you get these ones? That's a very tricky question. have, at this moment, only a handful of models that can be used to have a relation. However, this handful of models are calculated for circular orbits. So I have an eta and a beta for my models, and then I link that again to an analytical thing. And that analytics I put in here. But I only have a few models. I only have circle models. So we have later the maths, literally the maths of what would it be for an eccentric thing. We have, we need then to cancel, not to cancel it out, to integrate that and see what is happening. We don't have yet a good enough grid to have that very accurate. That's one of the next projects. But we have equations here, but I don't blame their highly accurate. And then you can say, haha, let's do the game. We are here, and this is the past, and that's the future of the star. What you see, I'll zoom in for its future. We were predicting that this is the orbital separation, and that's the radius of your M1 of the main star. You will see that they will collide. The companion will go into the envelope of your HB star. And then it comes towards the eccentricity, and here is a tension. Since, and now I go back to what Lea is also have been working on, we have a lot of, also in a group of Lea, for former group of Lea, that have been working on this kind of successes of post-AGB stars. And you see here for a small sample of barium and post-AGB stars, you see eccentricity versus period. And you see that many of them have quite a high eccentricity. Now, what do models predict? Models predict that given the wind masses weight, your system goes to the right. Given tidal interaction, it goes towards common envelope. And also, thanks to the tides, or thanks to tides, also circularize our system. Where is my system? The one that I cannot tell you about. It's there.
And the initial eccentricity is just what it was born with?
The initial eccentricity, now we have the current eccentricity, and we compute.
So it's eccentric because that's just how it was.
For these ones?
Yeah.
We don't know. That is what Lea has been working on. We see for the post-AGB stars, we see that many have an unexpected eccentricity, while models would predict them to be circularized, given the tides and given what we know. So people are often after extra physics that could pump up eccentricity. What we tell you here is, for an AGB star, that's the first time we have such a clear indication. Your indication was also roughly there. For the first time, we have a circular orbit here for an AGB star, and for the post-AGBs, I have an eccentricity. That's only one example. So it's a bit fluffy. It's only one example that tells you that potentially there is an eccentricity pumping mechanism at the end of the AGB or during post-AGB, maybe via its interaction with a circumbinary disk. But that's an offer. It's not a solved solution. In other sense, our system is also a bit weird. When I look to the precessors, the red giants, you see that my system stands there, while the red giants having low and high eccentricities in the log P eccentricity diagram do occupy model G. So you see that by starting having this one data point, we start to be triggered. And this is now a graph from Alan Jorissen from 2009, but I've added this one. So in Alan Jorissen's paper, you have the first two and the last two panels. And then Alan has clearly described it. You see a similarity between the second and my, almost last panel. Is that similarity, is that accidental, or is that a genuine? Is it like that there's not much happening between this phase and this phase? Or is it like that we have this phase and potentially something happens here, and then they go back there? Then you have an accidental similarity. Now we add our one data point. And so that seems to suggest that indeed there's extra physics. Physics from there to there, and physics from there to there. One is not a lot, but one is not. It's already solved.
Maybe a few minutes.
Yeah.
Finish is okay.
And then you were asking me about, yeah, but you asked me, I did know these are questions, not true. But eccentricity, you know, we are so much intrigued by the eccentricity since it has no circular eccentricity. Was it born circular or has it circularized? So let's do the computations. And so what you see here, we have done the computations for a lot of initial eccentricities. Oh, something misses here, that's not weird. And then you just follow the color. If it started blue, you look back to the blue and you see that our computations show that the eccentricity isn't changing much throughout its evolution. It implies that our system, given or take the correctness of these predictions, has been born circular. This is a challenge, since when you look to population statistics around main sequence stars, you have higher chance that it is eccentric than that it is circular. So either it is like that and we have such a system, or, and this is what I believe, something is still missing in the physics of circularization or the tidal physics or whatever. Somehow our systems seem too simple, and I don't believe that. So we think now we're now working on what kind of physics maybe is not in. So what's next? We're almost there. I can tell you many things. I can tell you about all new data that you'll be using, and for sure, ALMA, but also Gaia DR4 will be transformational there. We will have, and this is why I go to Santiago for the next part of my sabbatical, we will see literally with the epoch astrometry what these giant stars are doing, and we will be able to capture a lot of this binary statistics. Hydrodynamics comes into the coupling between grid-based and stage-based codes. Orbital evolution, that's the one, what we are after, and now this is now done already. We did not take the rotation of the star, the spin of the star into account. Since we thought, you know, it's a giant star, its spin is very slow, 2-3 kilometers a second. We neglected that as everybody. Now, together with Mats, we have put it in and it has an impact. It has an impact in the sense that we do not predict a common envelope evolution anymore. It has a lower impact on eccentricity. We are now starting to study the resonance coupling between the dynamical mode and the oscillation mode. What I can tell you already is that paper is ready, we will submit next week. If you have a companion and you want to understand the stellar structure, the internal structure, has a companion an impact, for instance, in the generation of your internal gravity waves? It does not. So luckily, you can continue your modeling. Yeah, it's a non-result, but this was important to check whether there is the dynamical mode versus the oscillation mode. And then the last thing is inversion theory, something I've been doing a bit while being here also in ONSAL. This is what we are after, at least this is where we live in, the non-ideal astrophysical scenario. I was telling you, we have so many sources for which we have the spectral energy distribution. I have far less sources for which I have the carbon line profiles, your line profiles. They do tell me already quite a bit of things about potentially binary. You see complex line profiles. These complex line profiles tell me that it's not a simple star, simple winds. But only for a few stars I have all my channel maps where I literally can see the complexities. So how to deal with that? Well, that's life. So we are currently developing with Owen, one of my other PhD students, we are at least working towards a nonlinear support vector machine. That is something that you can use if there is a nonlinear behavior between input parameter and output prediction. In our case, input mass loss rate, output or binary scenario, and output complexities. Yeah? If something is nonlinear, that's a mathematical tool that you can use, but you need to train. It's a kind of it's not really AI generated, but it has some flavors of that. So we are now working on larger data sets where we have morphologies and predicted line profiles. So we do the radiative transfer calculations with Marlies. That's been developed by one of my former PhD students. But then the trick is doing it backwards. Right? Doing it backwards is, well, I have ALMA data. Well, no, that was a prediction, but okay, live with it. Yeah? And I have line profiles. Can you tell me what was the inherent physical structure? So it's an image is radiation transport. That's not density. That's not velocity. We have done that. We have developed SPOM. BOM is a Bayesian inference code, model construction. You can have it agnostic, which it is. We can also put it with some priors into that, and it reconstructs, oh, but the quality of the screen is bad, density, temperature, and velocity. That's not yet real data. You know, that was trained on data, on synthetic data. So what I've now been doing while being here in Göteborg is, you know, I say, well, I have a lot of data here. I have a lot of carbon monoxide data. I have been discussing with Hans and with Alvira. Maybe last week we have been discussing in the group the NEST data set. If I have data, is it simple to say something upon mass loss rate? But then I need something that goes really fast. And that it works now. So you can't see it very well. But if you now have data, I can, on my simple laptop, I model 3 stars together, and after 4 hours, I have an outcome. I have the outcome of what is the mass loss rate. But I need now, so I go now really to the maths, since I need a fast mathematical routine before I can take it back to the support vector machine. And so this is now roughly working. There are still some things I would like to add, but I can do the reconstruction without looking at it. I can stay on and I do something else. Sometimes my laptop says out of memory, go laptop, but this is since I haven't ported it yet to my supercomputer in Leuven. But it works, so I'm happy. That's a nice outcome of being here. And so the idea now is the following. If we now have data, I have all of this carbon monoxide data. We have that for 800 stars. Can I, from the line profiles, have a discriminator that tells me it's a binary interacting or it's genuinely single? And using that information, having a predictor that tells me, and this is the associated mass loss rate with its uncertainty. And then if you can do that for many stars, you can play it back and say, well, for single stars, I have a mass loss rate relation. For binary stars, I have a mass loss rate relation. For the latter one, the uncertainty will be large. And so this is what we hope to achieve in the future, near future, new mass loss rate relations for AGVs and binary and supergiants that take that binarity into account, and that are better also for single stars.
Great, thank you very much. Okay, we have time for questions. Any questions? So raise your hands online or here. Any questions? And then, so Peter, please.
Cool. That's nice. So then, I had a few questions. Let me just. So when you compare your observations of the secret star to Amanda's models, the constraint on the current mass came from the luminosity, or where does that come from?
The constraint on the
models.
From the orbital inference or from Amanda Caracas?
You have your orbital mass.
Yes.
And then you compare to the models.
Yes.
How are you deriving the mass from the models?
That is based on a coupling between the linear pulsation code and stellar evolution code. So you're after this one, eh?
Mm.
Yeah. So this is here for this.
So it's based on the pulsation period.
It's based on the pulsation period. Yes. So the student of Amanda, Yoshi has been coupling the linear pulsation code, originally built by Peter Woods, with their stellar evolution code. So we use the pulsation characteristics. Then we can show it's a first overtone pulsator. We look to the growth rates of the pulsation mode. So it's a first overtone pulsator. And then you can link that with luminosity towards its mass.
Mm.
Yeah.
Let me try and, because I'm new to this field. So you said the binaries have a higher mass loss rate.
Yes.
So why is that?
Since there is gravitational interaction.
So you're pumping energy into the wind from the orbit.
Yeah, well, you have, no, so what's
or is it common envelope?
No, no, I cannot do that. Some people can't do that. So what is happening is, so you have this little dust grains, and they need from the AGB star, and they should be able to escape the gravitational potential of the AGB star itself. That's why you need the radiation pressure on them. On the other hand, if you have some gravity from the binary companion that helps sucking, it really literally helps in getting these grains out, and therefore it is increasing the mass loss rate. It's literally, if you have two body gravity, and you put that in your momentum equations and your energy, etc., you see that literally happening. It's the interaction with the gravitational potential of your secondary.
So most of the mass loss is flowing through the Roche lobe.
Yes,
secondary.
It has a mass accretion, mass transfer there is at least 15%. Then your companion is at 6 AU, so that's already quite far apart. 6 or 7 minutes. Yeah.
Okay, so I'll have to think about that. But so then, so why does this morphology change as you go to? You show this diagram of the increasing mass loss and it becomes more.
Yeah. So if you have higher mass loss rate, you often have a higher expansion velocity, so of the material from the AGB star, and then you can that's easy. Well, you can envision that, as I try to explain you, that if the speed is larger, your interaction period with your companion is lower. Say differently, if you have a low speed, your interaction time with everything, the gravitational potential of your companion is larger. And so you have much more time to interact. And meanwhile, the motion is ongoing. And that creates much more complexity in your structure than when it really goes fast. In terms of mathematics, if you would have to like to simplify it, even when you have your Bernoulli Hall accretion radius, that's literally 1 over v squared. Right? So your interaction length is smaller for a high velocity, and it's larger for a low velocity.
Okay. Great. Any questions online or other questions are here? So these are.
So connected to what you're talking about now. In the case that you have the binary, take a step back. So calculating the mass loss rate from a single star is already very difficult from first principles because of this whole transformation process in this very dynamic environment. It's very complicated. So I had first a question of how did you do that in your comparison that? And then the second is, when you have the binary, is the dust actually driving the wind, or is it you don't even need to form dust to have this?
Yeah. So the first thing is, for the simulation that you have seen, that was carbon dust. That's quite easy to form. So it's a carbon-rich star, and our grains are forming. So we can use the Bowen dust description. You can either use Bowen or you can go back to Sedlman. You get indeed your ab initio dust mass loss rate, and then we just put into if you put it in or not, is your.
But is this prescription that Lionel Sist also had for the?
Now we are using Lionel's prescription, but that simulation was already before Lionel. So Lionel is working with Phantom, that's ANAVAC that you have been seeing. And that was a simulation back from 2020 or something like that. And now we are currently comparing, that's nice, we're currently comparing SPH and liquid-based things. And we see similarities, which is good. And it's not an easy thing, but we see also different things. So it's very, we will maybe discuss it during Chile. We're still discussing with Owen whether to show it already. But we see in simple cases, one looks like the other. In more complex cases, there are differences.
Let's go to Kay's question next.
Yeah, hi Lynn, thanks for the talk. I find this binary thing very interesting. as you put it up, I mean, the masses are more or less the same. So you're saying that M1 is an AGB star, but your companion seems to be a little bit larger. Is this from the mass transfer or?
Oh, yeah, that's a very good question. I didn't touch on that indeed. So you see here a mass ratio slightly above 1. When we do the back calculations, it's clear indeed that we start, well, that initially M2 was slightly less massive than M1. And due to mass accretion, it has increased towards a mass ratio above 1. We are not sure upon what it currently is, whether it is a main sequence star or a white dwarf. We play with both examples in the Nature paper. I think my impression is that it is a main sequence star. We have far less chances of it being such a massive white dwarf. It will be a white dwarf of mass 1.2 solar mass or something like that. So in terms of statistics, I believe it more to be a main sequence star. We also haven't seen any strong indications in terms of UV or X-ray radiation, but we cannot completely exclude the white dwarf scenario.
Yeah, I mean, I find it even more interesting if it's a main sequence star, because it will become an AGB star pretty soon. So it will
Yes.
it will be even more complex when you have the secondary becomes an AGB star as well.
Yeah, I fully agree. Yeah, absolutely.
Okay, we have a few minutes left for the last two questions, so let's go to the end.
I'm just really curious, the orbital modeling that you're doing, how different would the parameters you derive be if you did not detect the companion? Is it something that you can even do if you didn't detect it? Like it seemed like you had the sort of four different times.
Yeah, that's so I go back so that it will help me if I show you this. So your question is?
If you didn't detect M2 here, could you still derive this same parameters, orbital parameters? Basically?
No, yes and no. So I'll say both explicitly yes and no. Why do I do that? Since you do see, and I didn't tell you about that, I have indicated some vectors here. Yeah, what are these vectors? These are the proper motion. I can't recall exactly. I think this is this is the observed in yellow is the observed proper motion by Hipparchus and by Gaia. In orange are predicted. But you see also that, so what is proper motion is nothing else than measuring how stars have moved. But you can also take the proper motion between the long-term proper motion between the green cross and the red cross. This is my long-term proper motion is the blue line, the blue vector. You see a difference between the long-term proper motion and the short-term proper motion between cyan and yellow color. That difference is an indication that you have an orbital companion, since it's that orbital companion that is moving the short-term proper motion. This has been used already using Gaia DR4 data to make up a catalog of potential binary candidates when the difference between cyan and yellow is more than 3 sigma. Yeah, that is good for close by companions that are fairly massive. Then you can see the impact on the proper motion. What will Gaia DR4 give you? So now we had 2 points. Yeah, so I'll go back to this part. So now we have 2 points, this one and this one. So we have Hipparchus and Gaia. Gaia DR4 will give you all measurements across time. So this is a kind of a mean value. Yeah. Whenever you see something like that, that will be extremely constraining on your binary parameters. So Gaia DR4 will really be a revelation when it comes to understanding binarity for all types of stars. The challenge will be that the Gaia DR4 catalog will give you the Keplerian solution, but the data will not be calibrated for our systems. What I mean is our systems are very bright with convective cells, and it will not take that into account in the calibration and in the catalog. So this is something I would like to do with Pierre Carvalho being in Santiago, developing routines, at least that we have accurate predictions for.
And when is that data coming again? Remind us.
End 2026.
Very good then. Well, I have many more questions, but I think we're at the hour now, so we should wrap up. But thanks again, Lynn, for a great talk and overview. And we look forward to the rest of your stay, and we keep chatting with you.
Okay.